Hello everyone. In this video, I'll evaluate a double integral using Green's theorem. So basically, Green's theorem is the following equality between a double integral of the difference of the partial derivative of the component of a function f over a region R and the line integral of the function f over the boundary C of the region R. So the region R is in the xy plane and C it's the boundary oriented counterclockwise. So let's apply this theorem to the following example. So we want to evaluate this double integral of this function x squared plus xy over the region R, where R is a square. So we have to look for for the component of a function such that the difference of the partial derivatives is equal to x squared plus xy. So let's describe the R, the square. So the region R is the square with boundary C, and you see it's oriented counterclockwise, and the C we can split it in 4 paths: C1, C2, C3, and C4, where C1 is starting from the origin O to the point A, and C2 from A to B, and C3 is from B to D, and C4 is from D to the origin. We need all these points to evaluate the parametric representations of each of these paths. So we take f1, one of the component, to be minus x squared y, and f2 to be 1 over 2y x squared. So we calculate the derivative of f1 and derivative of f2 and take the difference and to get x squared plus xy to use Green's theorem. So we have the double integral. This is the difference of the partial derivatives is equal to the line integral over C of this is f1 dx plus f2 dy. This also can be written with the dot product between these two vectors. This is f1 and this is f2, dot product dx dy. Now if we make a change of variables, taking r to be the vector xy, we can write this line integral as the line integral over C of the function f of r dr, where f is equal f1 f2 is a vector with f1 f2. Now we can split this former integral into 4 integrals over the C1, C2, C3, and C4 with parametric representations R1, R2, R3, and R4 consecutively, and having the same orientation as C, which is counterclockwise. Now the parametric representation of C1, it's between from A to A, will be OO plus T OA, which is 0, 0 plus T1 minus 1 is equal to T minus T, where T is between 0 and 1, and C2 is the path from A to B, can be written as the parametric representation can be written as the sum of these two vectors OA plus TAB, and then evaluate OA, which is 1 minus 1, plus T, evaluate AB, you get 1, 1, and then the parametric representation C2 will be 1 plus t minus 1 plus t. The same thing for the parametric representation of the path C3, which is from B to D, will be OB plus T BD, which is 2 0 plus T minus 1 1, and this is equal to 2 minus TT, where T is between 0 and 1. And the same thing for the parametric representation of C4, R4 will be 1 minus t, 1 minus t, and t between 0 and 1. And then we evaluate now the line's integrals one by one. So the line integral over the path C1 will be the integral from 0 to 1 f r1 r prime 1 t dt. This is just the differential dr1, okay, which is the derivative times dt. Then we evaluate f of r1, which is t cubed minus 1 over 2 t cubed, the dot product of r prime 1 of t, which is 1 minus 1 times dt. We multiply the component and we add them up, we got 3 over 2 t cubed, and then we integrate to get 3 over 8. Now the line integral over C2 of the function f will be the integral from 0 to 1, evaluating f at r2 and then replacing dr2 by the derivative of r2 times dt, then evaluate f of r2 to get this vector, then the dot product with the derivative of r2 times dt, then evaluate the dot product between these two vectors, we get minus 1 over 2, the integral from 0 to 1 t cubed plus t squared minus t minus 1. We integrate 1 by 1 to get 11 over 24. Now the same thing for C3, we evaluate f of r3 dot product r prime t dt. This is f of r3t dot product of the derivative of r3, which is minus 1 1. Evaluate, you get 11 over 8. The same thing for C4, evaluate f of r4, then the dot product minus 1 dt to get 1 over 2, the integral from 0 to 1, 1 minus t cubed dt. And then evaluate the integral to get 1 over 8. Then the line integral now, the former integral over the whole path will be the sum of all those three lines integrals, 3 over 8 plus 11 over 24 plus 11 over 8 plus 1 over 8 equals 7 over 3. And this is the same value we found on the previous video when we evaluate this double integral using a change of variable. And that's all, folks. Thank you very much.